Okay, let's go ahead and get started. Sorry for the delay. Just having some computer problems up here. Okay, let's go ahead and get started, which means, please, thank you. Keep your conversations amongst yourselves at a lower volume. Thank you. Lower than that, please. Thank you. Okay. So let me remind you of where we left off last time. So last time we learned about two of the most important effects of general relativity, which were consequences just of the equivalence principle. And the first effect was that of gravitational redshift, which says that if I am deep within some gravitational potential, and I send you a photon or some sort of electromagnetic wave, a signal, at a given frequency, then the frequency of the signal that you receive will differ from the frequency of the signal that I sent by an amount which is equal to 1 minus the difference in the gravitational potential between us divided by c squared. So the slogan that you should remember is that radiation sent to you, or waves sent to you from deep within a gravitational potential, are redshifted. So if I send you a light signal, which is blue light, then you would observe it as being redder than the signal that I sent you. And likewise, we discovered the effect of gravitational time dilation, which is a closely related effect, which states that if I, sitting here deep within a gravitational potential, have a clock which is ticking, say, once per time interval t1, and you have a clock that's ticking once per time interval t2 at some different location, then the rate at which those two different clocks tick will not necessarily be equal, and will be related to one another by this same gravitational gravitational factor, 1 minus the potential difference divided by c squared. So, for example, if you have a spherical mass such as the Earth or the Sun, let's say the Sun has mass m, then the gravitational potential around the Sun is gm divided by the distance to the Sun. And so this gives you a way of estimating the gravitational redshift and gravitational time dilation of effects, say, in solar system physics. And indeed, both of these effects that I have described for you have been observed. Gravitational redshift was first observed in the 50s. Gravitational time dilation a little later, but it's a very important effect. And one of the most important and, I think, disturbing implications of these effects of gravitational redshift and gravitational time dilation is that you can see that clearly something goes wrong, or I should say, something funny happens when you're at a radius such that this factor, delta phi over c squared, is of order 1. Now, you can see that when that factor is exactly equal to 1, these formulas for the gravitational redshift and gravitational time dilation become rather singular. In particular, we would predict that there would be an infinite time dilation factor and an infinite gravitational redshift factor. But I've said approximately equal to 1 rather than exactly equal to 1 because in this regime where you have a very, very strong gravitational effect, we wouldn't necessarily expect that these formulas which were basically derived using Newtonian physics and the equivalence principle, would remain valid. Now, it turns out that there's a way of guessing what will happen when the radius is very, very small, so that this gravitational time dilation factor can become 0. And in order to do so, let me remind you of what we began discussing last time, which is that these formulas allow us to guess the form of the invariant interval in the presence of a massive object. How does that work? Well, we just remember that the invariant interval is what we use in order to measure the proper time separation between two events. That is to say, it's the thing that we use to measure the rate at which a clock ticks in relativity. And it's equal to minus c squared times d tau squared, where d tau is the proper time interval between two events. And using the expression for gravitational time dilation that I wrote down for you earlier, you can guess that this should be something like minus c squared times that gravitational time dilation factor times d tau squared, plus higher order terms that we really don't know how, or I guess I should say dt squared, if t is the time measured out in infinity. And this is what I derived for you at the end of class last time. And I don't want to spend too much time dwelling on this formula, okay, because this is not really a class on general relativity. But I do want to point out to you that indeed in this expression, we can see that something deeply disturbing happens when the radius is equal to 2gm divided by c squared. And for an object of mass m, this is a very special radius which plays an important role in general relativity, known as the Schwarzschild radius, or Schwarzschild radius. I never actually know what the right way of pronouncing his name is. And it is a distance scale which allows you to estimate the size of effects of general relativity for a given mass of a given radius. So, in particular, you see that in our expression for the invariant interval ds squared, you get a 0 in front of dt squared when the radius is equal to the Schwarzschild radius. So, indeed, as I think many of you have probably anticipated, the funny thing that happens is that one has an event horizon, and the object that we are describing is nothing more and nothing less than a black hole. And what I want to do for the rest of class today is at least sketch for you and give you a very, I would say, phenomenological introduction to the theory of black holes and a few of their interesting features. But before I do so, I should tell you exactly why this is so uninteresting. So the reason why this expression that I have derived here is uninteresting, at least for normal objects, such as the Earth and the Sun, the Schwarzschild radius is tiny. Okay. So, the expressions, say, for gravitational redshift and time dilation assumed that we were in vacuums. And what do I mean by that explicitly? I mean that they were derived assuming that you were in empty space with matter nearby, which is creating a gravitational potential, but that you weren't inside the matter itself. Okay. Inside, what's the phrase by Groucho Marx? Outside of a dog, a book is a man's best friend, but inside of a dog, it's too dark to read. Okay. So inside of a dog, the expression for the gravitational redshift and time dilation that I have written down here actually failed to apply. Okay. Indeed, if you want to ask whether this funny business at the Schwarzschild radius is important, say, for the Earth, what we need to do then is calculate the Schwarzschild radius of the Earth and compare it to the actual radius of the Earth. Okay. Now, I don't want to completely give away the answer because it's something that you are going to compute on the problem set due Wednesday. And for the Earth, however, it turns out that the Schwarzschild radius is of order a few centimeters. I don't actually remember what it is exactly, but you'll discover it for yourselves if you haven't already. So that means that as far as studying the physics around the Earth, in order for there to be all of this infinite time dilation and infinite gravitational redshift, you would need to squash the Earth down to the size of a few centimeters. And likewise, for the Sun, the Schwarzschild radius is of order a kilometer or so, a few kilometers. I don't remember exactly. And again, the Sun, as you may have heard, is much bigger than a kilometer across. Okay. So let's ask then, just for the purposes of this class, what happens if we have an object which is so dense that its physical radius is less than or equal to its Schwarzschild radius, which, I remind you again, was twice Newton's constant times the mass of the object divided by c squared. Maybe before answering that question, let me just make one more comment about this formula. Aside from that factor of 2, this is a formula that we derived on the first or second day of class this semester. Because if you just think about dimensional analysis, and you say, what quantity with dimensions of length can I form out of mass, speed of light, and Newton's constant, this is the only thing that you can form. You know, that number 2 that appears out front, that's some special feature of general relativity and our particular theory of gravity. But just based on general dimensional analysis reasoning, you know that this is the typical length scale, the typical distance scale, at which general relativistic effects are going to become really important. And indeed, even for non-black holes, things like the Earth and the Sun, you can use this dimensional analysis reasoning to derive all sorts of interesting effects, such as those observable effects of solar system physics that were the primary original experimental tests of the theory of general relativity. But let's just spend a few more minutes thinking about what would actually happen if we had an object that were so dense that it was inside of its own Schwarzschild radius. So the first thing that you'll notice is that according to our expressions for gravitational redshift and gravitational time dilation, the time dilation and redshift factors will become infinite. So the idea is that let's say that we have some black hole here. Okay. So this is some black hole. And we're sitting out here. safely far away from the black hole, but we throw a graduate student into the black hole. And this graduate student, they don't get paid nearly enough, the graduate students here, for the kind of dangerous work that they have to undertake. And this graduate student is loyally sending back information to us outside the black hole about what he or she is experiencing as they fall through the event horizon of this black hole. So the first thing that will happen is that the redshift factor, as they cross the event horizon of the black hole, will become infinite. So the light that they send back to us will become redder and redder and redder until it's infinitely red, infinitely long wavelength, as they are crossing the event horizon of the black hole. And the second thing that will happen is that the gravitational time dilation experienced by this graduate student relative to us will actually become infinite. Now, why does that happen? Well, or what does that mean? Well, it means that as this graduate student is sending us their signals, they're saying, well, now it's 12 o'clock, it's 1 o'clock, it's 2 o'clock, and so forth. For us, sitting out here at infinity, it might take us a month or a year for a single hour to pass for this graduate student as they approach the horizon of the black hole, until eventually they will just appear to us to be frozen in time near the event horizon of the black hole. So, you might think, then, that life is rather unpleasant for this graduate student crossing the event horizon of the black hole. But, in fact, at the time when they cross the event horizon of the black hole, life might, in fact, be okay. And the reason is that for a very big black hole, the force felt by this graduate student at the event horizon which again is given by 2gm over c squared, might be very small. Why is that? Well, let's just make a very simple Newtonian estimate of the force felt by this graduate student. Well, remember, the force felt by someone, a distance r from an object of mass m, is proportional to m over r squared, times some constants, which I'll ignore just to make a parametric argument for you right now. And you can see from our formula for the Schwarzschild radius that the Schwarzschild radius is proportional to m. So this goes inverse with the mass of the black hole. So for a very large black hole, the event horizon is not a particularly dangerous place. Indeed, you might not even notice if you fell through the event horizon of a black hole, if the black hole were sufficiently large. We could be falling through the event horizon of a black hole right now. Indeed, if the current theories of cosmology are correct, we are passing through event horizons at every moment as we speak, because these are not black hole event horizons, but as we will see later this week when we get into cosmology, they are different sorts of event horizons that are, in fact, not so different from black hole event horizons. Okay, so if a black hole horizon is not a particularly dangerous place in and of itself, why do we make such a big deal of it? It's a place where the gravitational redshift and gravitational time dilation factors become infinite. And there's one other important feature of the black hole horizon, which is that it is what is known as an event horizon. Now, we've already actually encountered an event horizon once before in this class, when we considered our constantly accelerating observer in special relativity. And to understand why the Schwarzschild radius is an event horizon, let me just write down this formula for you again, which we guessed last time. And let's stare at that formula and think about it for a second. Okay. So first of all, what does this formula look like when the radius is very large, when you're very, very far from the black hole? Okay. So let me rewrite this formula a little bit as 1 minus the Schwarzschild radius divided by your position. So you can see then, if r is much bigger than the Schwarzschild radius, that is to say, if you're very far from the black hole, ds squared is minus c squared dt squared plus some other stuff. Okay. That's the usual formula. That just says that if you're very far from the black hole, you can forget about it. It doesn't really matter very much. Your clocks tick exactly as they've always ticked, and there's nothing particularly interesting going on. However, as r approaches the Schwarzschild radius, this factor, 1 minus rs over r, goes to 0. And indeed, for r less than the Schwarzschild radius, this factor is negative. So what does it mean that it's negative? Well, remember that in our expressions for the invariant interval of special relativity, ds squared was minus dt squared, and that negative sign was very important. For example, it meant that if you stayed at fixed position, you were on a time-like trajectory. Time-like because the invariant interval was imaginary and the square of the invariant interval was negative. However, we see now that if you're inside the event horizon of a black hole, that factor becomes negative. And so if you stay at fixed position and go forward in time, you're not moving on a time-like trajectory, you're moving on a space-like trajectory, one where ds squared is positive instead of negative. So what does that mean physically? That means that inside the event horizon, where r is less than the Schwarzschild radius, you have to travel faster than the speed of light in order to stay at the same location. So if you're outside of the black hole, let's say that I'm 10 times the Schwarzschild radius from the black hole, then the black hole will be pulling me towards the event horizon. But it would be possible for me to be in a rocket ship that is resisting the pull of the gravitational pull of this black hole. And as I get closer and closer to the black hole, then this rocket ship will have to accelerate faster and faster in order for me to prevent from being pulled inside the black hole. And the event horizon is the place where that no longer becomes possible, where you would have to be traveling faster than the speed of light to escape from within the event horizon. And in fact, as you will or have done, depending on how diligent you are, for your next problem set, you're going to work through that analogy more precisely. You'll study a planet, and you'll calculate the escape velocity of the planet, and then you'll ask what density that planet would have to have in order for the escape velocity to exceed the speed of light. And you'll see that indeed this gives you exactly the same notion of an event horizon that we've described here. Question? Well, there's a question here first. Yeah.
I'm a bit confused. Should RS be Gn over 6 squared or 2Gn over 6 squared?
RS is 2GMC.
But in our expression for gravitational
Yes. Remember, that's an important point. Remember that I told you that we shouldn't exactly trust these expressions for gravitational time dilation and gravitational redshift when you're near the event horizon of a black hole. So in fact, it turns out that the correct so for doing things like solar system physics or GPS or something like that, these expressions are just fine. But one of the things that I kept reminding you of last time is that when gravity is very strong, we don't necessarily trust these expressions. So indeed, just based on these expressions, you would think that the event horizon of a black hole happens at a radius which is gm over r, not 2gm over r. But in fact, it turns out that in general relativity, all of this stuff happens at a radius of 2gm over r. Now, I've motivated this discussion of black hole physics using these sort of simple formulas for time dilation and redshift, because those are the formulas that we can easily derive just by using the equivalence principle. And it turns out, in fact, as is often the case, that the answers that you get are qualitatively correct, but they differ in some very small details from the actual answers. That's an important point. Good. There was another question. Was it the same question?
No.
Okay.
So if you are inside of the Schwarzschild radius, then
yes,
it's impossible to leave.
That's correct.
But if you are on the outside, it seems like it's also possible to get into the inside.
That is not correct. Okay. So why would you say that?
Well, because the 1 minus RS over R is approaching 0.
Yes.
As you near the Schwarzschild radius.
Uh-huh.
And then on the inside,
yeah,
there's a space like a separation.
That's right. So the idea. So maybe I can answer your question by telling you the following, or maybe this will just confuse the issue even more. Okay. So I haven't written down for you the full expression for the invariant interval in general relativity around a black hole. So let me just write it down for you without any derivation. Okay. So there's the term that we met already. And let's say that we want to understand how this invariant interval changes as a function of radius. So you want to move radially. Then it turns out you have the inverse of that exact same expression there. So for example, in order to analyze, how much force you would feel in general relativity as you cross the event horizon, you would need to take both of those terms into account. And the thing that you notice that is very, very perverse about this expression is that when you're inside the event horizon, so far from the event horizon, 1 minus 2gm over c squared r is positive. The coefficient of dt squared is negative, and the coefficient of dr squared is positive. That means time is time and space is space. Okay. Inside the event horizon of a black hole, 1 minus gm over c squared r is negative, so the coefficient of dt squared is positive, and the coefficient of dr squared is negative. So inside the event horizon of a black hole, time and space, in a sense, interchange roles. Okay. I should really put that statement in quotes, because at this point, it doesn't really mean very much to you. And unless this were a class on general relativity, it couldn't mean very much to you. But I just like saying this because it really makes it clear that in relativity, time and space really are on equal footing. And why time is time and space is space is not an assumption of the theory, but rather it is a consequence of the theory. It's a consequence. The fact that time is time and space is a consequence of the fact that we're in a part of space which is not inside a black hole event horizon. And inside a black hole, those different notions would get mixed up a little bit. Okay, so that's just a bit of vague words that don't mean very much. But hopefully it gives you at least a little bit of a flavor for what life would be like if you were to jump into a black hole. So let me actually end this discussion by telling you a little bit about the role of black holes in physics today. So, of course, the Sun, the Earth, Jupiter, and so forth are not black holes. And the reason is that for normal objects, the internal forces that govern the structure of that object prevent them from collapsing into black holes. In the Earth, for example, all of the matter that makes up the Earth has some inherent pressure which makes it want to occupy a large volume, which keeps the Earth from being crushed into a sufficiently dense object in order to form a black hole. But as you look at more and more massive objects, the force that is required by the material that makes up that object to prevent it from collapsing into a black hole is greater and greater. So, for example, for a star, the forces that prevent the star from collapsing into a black hole is the nuclear forces that give the star all of its energy. So, for example, in the Sun, there is some fusion going on between the various elements of the Sun, hydrogen and helium and so forth. And this fusion gives all of the atoms and molecules in the Sun lots and lots of energy, so they want to keep inflated. It's just like if you had a gas and you heated it up to a very high temperature, or you pumped a lot of energy into it, the gas would want to expand. Okay. And so for stars, it's that process of ongoing fusion in the core of the star that gives the star enough energy to keep its size large enough to prevent it from collapsing into a black hole. The question then is, what happens when the fuel for fusion runs out? So in a star, for example, such as the Sun, there's hydrogen that's fusing into helium, helium that's fusing into neon, and so on and so forth. But that process has to stop eventually as all of the available hydrogen, helium, and so forth gets fused together. And at that point, something dramatic is going to happen because the gravitational forces that want the star to collapse in on itself suddenly are going to take over. Usually when that happens, there's something very dramatic, such as a nova or a supernova. And the remnant of that can be one of either three possible objects. Okay. So the first thing that can happen is that the star, when it runs out of this nuclear fuel, can collapse into a white dwarf. Okay. So what is a white dwarf? A white dwarf is a giant atom. What do I mean by that? Well, what is an atom? It's a bunch of protons, neutrons, and electrons. And indeed, the electrons, inherently have within them some pressure, which keeps the electrons from collapsing down into a black hole. So, for example, if you think about the models of atoms that you might have learned in your high school chemistry or physics classes, one of the things that you learned is that Electrons don't want to be in the same place because of what's known as the Pauli exclusion principle. This is what's responsible for all of chemistry, for example. And it's this pressure that keeps electrons from wanting to be in the same place, known as the electron degeneracy pressure, which keeps the star inflated. And in particular, it keeps it from collapsing further into a black hole. So in order for a star to form a white dwarf, the force of gravity that makes this thing want to collapse can't be so strong that it would overwhelm the electron degeneracy pressure. And so the mass of the star has to be less than about 1.5 solar masses. And this number, 1.5 solar masses, is what's known as the Chandrasekhar mass. Indeed, it tells us that eventually our sun will collapse into a white dwarf rather than a black hole. Question?
When you're saying it's a giant atom, are you saying that all the electrons on the surface of the white dwarf?
No, I don't mean that all of the electrons are on the surface of a white dwarf. What I mean is really, so what is an atom? An atom is something made out of protons, neutrons, and electrons. Okay, that's what I mean.
If the pressure is too high, can't you have like a density ionized, so there's no nuclear?
Yes, that's what we're getting to next. Okay, that's what's going to happen next. Question?
1.5 solar masses, is that before or after the...
That's after the collapse. So, for example, this is one of the most famous computations in physics, really. This calculation of 1.5 solar masses involves an incredible amount of physics. You need to know general relativity, of course, to understand this gravitational pressure of this relativistic object. You need to understand nuclear physics. You need to understand atomic physics. It's good stuff. It's a real, this is, when considering things like white dwarfs, neutron stars, and so forth, these are objects for which many, many different theories of physics all suddenly come together. And this is one of the reasons why they're so interesting to us. Okay, so what happens if you're too massive to form a white dwarf? Well, indeed, what will happen? So if you have a bunch of protons, electrons, and neutrons all hanging out together, and you subject them to a huge force trying to squash them into a small region, then what's going to happen is that the protons and electrons are going to find each other. They're going to be squashed together, and a proton has positive charge, an electron has negative charge. So when they're squashed together, they'll form a neutron, which has no charge. So when you think of a neutron star, you shouldn't think of a giant atom. You should think of a giant nucleus of an atom. Because in that case, what's happened is that all of the electrons and protons have been squashed together to form neutrons. And just as electrons don't like to be in the same place, which forms some degeneracy pressure that keeps them apart, the neutrons themselves will experience a degeneracy pressure, which will keep this object from collapsing. And indeed, neutron stars are observed, okay, just as white dwarfs are observed. They're known as pulsars. Why are they called pulsars? Well, because typically when these neutron stars form, they have some magnetic field which causes them to beam particles out in radial directions, and they'll be rotating rapidly around some axis. And if you happen to be standing here in the line of one of these neutron stars, where you get hit by the beam of particles as it rotates by, then it's an object that will appear to pulse rapidly. And so when we see these pulsars, you can measure their timing, you can measure their luminosity, and you can learn all sorts of interesting features of these objects by studying in detail the properties of these pulsars. Okay. And these pulsars are formed from objects whose mass ranges between 1.5 solar masses and a number which is actually not known terribly well, but which is about 5 solar masses. By the way, sorry, I shouldn't have used that notation. In astronomy or in astrophysics, it's typical to draw a circle with a dot through it when you want to say sun. Okay, let's write down sun. I should actually make one comment, which is that pulsars and neutron stars currently provide some of the best experimental evidence for general relativity. So, for example, the detailed timing experiments of pulsars, and in particular of binary systems containing 2 pulsars that are orbiting around each other, provide some of the most detailed and accurate tests of the theory of general relativity. And at this point, when we want to consider more heavy objects, the theory of these objects actually becomes a little murky. Okay. So in particular, nuclear physics, namely the physics of nuclei, i.e. the physics that you would need to understand in order to understand the dynamics of a neutron star, is not nearly as well understood as atomic physics. So we don't know exactly when it is a neutron star will collapse into a black hole, but it's believed to be at around 4 or 5 solar masses. And if the mass is larger than or equal to 5 solar masses, then the object will form a black hole. And black holes are observed. Okay. They're not observed directly, because of course, not even light can escape from within the event horizon of a black hole. But they're observed indirectly. So, for example, people can find stellar remnants, namely the remnants of stars that have collapsed into putative black holes. And they can study the dynamics of the objects orbiting around the stellar remnant. And based on the dynamics of the objects orbiting around the stellar remnant, they can determine the mass of the stellar remnant. And they can also determine its size simply by looking at what's there, at how close things are orbiting in next to the stellar remnant. And based on this, they can conclude that there's some object which is sufficiently dense that it should be a black hole. So there are indeed some indirect evident observations, because of course you can never see light coming from a black hole, of stellar black holes with masses that are in the right range, namely larger than about 5 solar masses. I should make 2 more comments before we end. The first is that it's certainly possible, and nobody really knows for sure, that there are other sorts of objects that are denser than neutron stars, but which haven't quite gotten dense enough to collapse into a black hole. So as I said, we don't have a truly precise understanding of nuclear physics in the regime where one would want to study these neutron stars. So, for example, these neutron stars are fantastically dense objects. Okay? And we don't really have a great understanding of what nuclear matter does at such high densities. Okay? You know, people at Los Alamos or somewhere like that might be very interested in understanding what nuclear matter does at very high densities. But it's a subject about which we as physicists still have very imperfect knowledge. So one of the things that people like to imagine is that there is some new phase of matter where these nuclei will bind together in some curious way, and form some new type of object. So, for example, people have even postulated that there's something called a quark star, where the constituents of the neutrons, which are, of course, quarks, will themselves support the star and keep it from collapsing, just as they did for a neutron star. Indeed, this is one of those fascinating areas where both general relativity and nuclear physics, particle physics, all come together. So it's a really fascinating place for us to probe our understanding of various of the most interesting theories of physics. And let me conclude with one final comment, which is that in addition to stellar black holes, there are also black holes at the center of each galaxy. So, for example, at the center of our galaxy, there's a black hole with a mass of about a few 100,000 or a million solar masses. I don't remember. So these typically have a mass of 10 to the 5 or 10 to the 6 times the mass of the sun. And indeed, although we can't see any radiation or signals from inside of the black hole, the disturbances that these black holes create as matter swirls around to fall inside the black hole are some of the most energetic objects in the universe. So the picture that you keep in mind is that you have some black hole here, and that you have some matter which is orbiting around it, swirling in to form the black hole. So it's all falling into the black hole. And this matter forms a disk known as the accretion disk. Sorry, I can't spell correctly. The accretion disk around a black hole. And that matter is subject to hugely, fantastically strong forces, which create radiation. And just as with the pulsar, this radiation is beamed in the directions transverse to that of the accretion disk. And if you happen to be out here looking at this beam of radiation, it would look to be a fantastically bright object. And indeed, such objects were discovered long before they were known to be black holes, and they're known as quasars. And they're among the brightest objects in the universe. Yes?
So are these black holes not massive enough that the force is low, like you said?
I'm not going to answer that question because you will on your next problem set. Okay. Good question, though. Okay, I should probably stop here. I'll see you guys next class where we go into gravitational lensing.